The balanced chemical reactions and equations we've looked at so far have been molecular equations. We need to talk about molecular, total ionic, and net ionic equations and what these different things mean. So, to analyze reactions, it often helps us write equations in three different ways to really see what's going on. Again, the molecular equation is what you guys have seen so far. A molecular equation is where every compound is written out in its neutral form. So, let's say I'm going to react silver nitrate, AgNO3, and I know that's aqueous because I know my solubility rules, with sodium chloride, NaCl. Again, I know that's aqueous because I know my solubility rules. And this would produce silver chloride, which is an insoluble salt, and sodium nitrate, which is aqueous because I know my solubility rules. This is my molecular equation. Every compound is written out, every compound's in its neutral form. The two other forms we have are called total ionic and net ionic. Total ionic equations. In order to write a total ionic equation, you ask yourself, is this species a strong electrolyte? Remember what your strong electrolytes are. Your strong electrolytes are your soluble salts, your strong acids, and your strong bases. So if they are a strong electrolyte, we write them out as separate ions. What I mean by that is when I look at like silver nitrate is a soluble salt. So instead of writing AgNO3, I would write Ag plus aqueous plus NO3 minus aqueous. So I've written them out as separated ions. I look at my next species, sodium chloride. That is also a soluble salt. So that splits up into sodium ions and chloride ions. Next up, I have silver chloride, and that says solid, meaning it's insoluble. It is not a strong electrolyte. It is, in fact, a weak electrolyte. We'll talk more about that in Chem 2, but we leave that together. So AgCl, solid, stays together. And then my sodium nitrate is a soluble salt, so I'm going to split that up and write Na plus and NO3 minus. So the total ionic equation includes all the species written out, how they exist in actual solution. What this means, again, is if I have a beaker, and in this beaker, I have mixed together silver ions, chloride ions, sodium ions, and nitrate ions, the moment the silver and chloride find each other, they're going to form silver chloride. So they're going to form that in solution. I will no longer, and then precipitate out a solid silver chloride at the bottom of my beaker. And so I no longer have silver ions and chloride ions in solution. I just have the sodium ions and nitrate ions floating around. The silver ions and chloride ions that were originally there are what paired up to form my solid. Your net ionic equation, you remove the spectator ions and you're removing them from your total ionic equation. So you got to recognize your spectators. Spectator ions are the species that are present on both sides of the reaction. So I look through it and I say silver plus. Do I have silver plus on the other side? No, I do not. So it must not be a spectator. So I'm going to go ahead and write silver plus aqueous down here. I then look and I see nitrate and I say, is nitrate on the other side of the reaction? Absolutely. That is a spectator. So I'm going to go ahead and cross that out. I'm not going to put that in my net ionic equation. Next up, I see sodium ions on both sides of my reaction. So again, sodium is a spectator here. Then I see the chloride ions, but there's no chloride on the other side. So I'm going to write plus Cl minus aqueous. And the last thing I have is on the product side, silver chloride solid. So my spectators here or Na plus, which is sodium ion, and NO3 minus, which is nitrate. So why do I care? Why is this important? If you look at that net ionic equation, it's telling us something very important. It's showing the driving force of the reaction. It's showing what's actually happening, but it's showing us why the reaction proceeds as written. If everything floating around in there formed aqueous on the other side, it wouldn't actually form anything. There'd be no reaction. The net ionic equation shows you the driving force behind the reaction. Let's do a couple examples. The first one up, we have acetic acid reacting with sodium hydroxide. Remember, acetic acid is a weak acid, meaning it only partially dissociates in solution. Only a percentage of the sodium or of the acetic acid molecules will break apart and ionize, forming acetate and protons. Sodium hydroxide is a strong base, and because it's strong, it will ionize 100% in solution. It forms sodium acetate, which is a strong electrolyte because it is a soluble salt. Not only is sodium ions always soluble, acetate ions are also always soluble. Remember, your strong bases are also strong electrolytes, and your weak acids are weak electrolytes. And then water, which is a non-electrolyte. Technically speaking, it's actually a weak electrolyte. We'll get more into that in Chem 2. Um, it is actually, technically speaking, a weak electrolyte. But again, we'll deal with that more in Chem 2 than we do in Chem 1. So now that I've written all that out, I'm going to erase it all because we need the space. So split up your species that are strong electrolytes. Again, this is your strong acids, strong bases, and soluble salts. Acetic acid is not one of those. It is a weak electrolyte, so we leave it together. CH3, COOH, and aqueous. Sodium hydroxide is strong, so we're going to split it apart. Na plus and OH minus. Sodium acetate is a soluble salt, so we split it apart. Na plus, CH3COO minus, and then water. Again, this is your total ionic that I just wrote. Until you get comfortable writing them, I recommend you write out the whole thing. Now let's think about what species are doubling up, which are spectators in the solution. I've got acetic acid only on one side of my reaction. So acetic acid must be in my net ionic equation. I see a sodium ion on the reactant side, but I have a sodium ion on the product side as well, so sodium must be a spectator. The sodium ion specifically, not sodium metal, sodium ion specifically is a spectator. I've got hydroxide on my reactant side, but not my product side. And that's all the reactants I have. So if I've canceled everything correctly, everything else listed on the product side should be in my overall reaction. And we get acetate and water. So the driving force for this reaction, the reason it goes forward, is the formation of water. And that is the driving force anytime you mix an acid and a base. Acids and bases neutralize one another to form salt and water. Go ahead and pause the video if you need to write that down, because I definitely do erase this. It's very busy and I need to be able to work on the second example. Okay. Next up, we have Ki, which is potassium iodide. Now, iodides are not always soluble, but potassium is an alkali metal group 1, always soluble. So it is a strong electrolyte, as it is a soluble salt. Br2 is just a molecular compound, diatomic, not an electrolyte. It's not a cation-anion combination. It's not a strong acid, strong base, or salt. It's forming potassium bromide, which is a strong electrolyte, soluble salt. Again, potassium group 1, alkali metal, always soluble. And then iodine, it's a diatomic molecule and a non-electrolyte. So when I look at this, the only things I can split up is my strong electrolytes. I have K plus, aqueous, but notice I have the 2 in front there, so I have 2 of them, plus 2I minus, aqueous, Br2 liquid, and this gives me 2K plus, aqueous, 2Br minus, aqueous, and an I2 solid. If I look here, the only spectator I have is K plus, or the potassium ion. The driving force of the reaction is the formation of I2. So that's why the reaction occurs, is to form I2. Again, this is the total ionic. So my net ionic would be 2 moles of I minus reacting with Br2 liquid, forming 2 moles of Br minus, so the bromide ion, plus I2 in the solid phase. And the last example we have here, so I need to erase this. Calcium carbonate reacts with hydrochloric acid, to form calcium chloride, water, and carbon dioxide. The driving force of this reaction is the formation of not only water, but also carbon dioxide. The only spectator I have here is Cl minus, the chloride ion. So you can write out the full net ionic if you, or the full total ionic if you need to, but if you recognize what's being formed and what it's being formed from, it can oftentimes get you there a little bit faster. Calcium carbonate is a weak electrolyte. It is not soluble. Hydrochloric acid is a strong acid, so it is a strong electrolyte. Calcium chloride is a strong electrolyte because it is soluble salt. Water and CO2 are both molecular compounds. So my net ionic here would be calcium carbonate reacting with 2 moles of H plus and forming calcium 2 plus ions, water, and CO2 gas. Again, the calcium 2 plus ion does exist in solution. It's floating around. The H plus exists in solution. It's floating around. It's that if I take the solution away, if I take the solvent away, the water away, then I would have, calcium chloride in the solid phase again. When it says aqueous, it means that they're floating around in solution. And you just have to recognize the strong versus weak electrolytes.